Hi everyone, I welcome you to this video series on Ensemble Methods. I'm Bharath Reddy and this is a part of Machine Learning Bootcamp. In this video series, I'm going to talk about Ensemble series. This would be a 5-part video series where in part 1 we develop intuition around what these ensemble methods are. In the second video, we cover and develop intuition on random forests. In the third video, we understand what bagging methods are. In the fourth video, we would discuss boosting techniques. And in the final video, we conclude of the series by taking a hands-on example and working it on Jupyter Notebook, covering everything that we would have learned so far. With that being said, ensemble methods, just like decision trees, uh, can be used to can be applied on both regression and classification problems. If you have not seen the video series on decision trees and cart, I would suggest you first cover them before going through these videos. Ensemble machines are machine learning methods for combining predictions from multiple separate methods or models. So far, what we have learned is to create a single model and use it on a data set and developing some predictions. The central motivation for ensemble methods is rooted under the belief that a group of algorithms working together can often perform better than a single algorithm. Now, usually, all the models would belong to a particular family of models, but they don't have to be. Uh, the usual way these are developed is we take multiple machine learning models and we train them on the same data that we have, and once these models are trained, we pass our testing data to each of these models and we take predictions from each of these models and we combine these predictions to get an output. What we see is output, the combined prediction is often much more reliable and robust than prediction from any single model. Let's see how this works. So let's say by some way we are able to create multiple models, each a little different. We'll get to the details of how we develop these multiple models a little later, but for now, think of these as each of these model as a different decision tree, all built on the same model. Now there are many ways to build these models, build these trees from same data, but remember one thing, these trees have to be a little different from each other. I'll come to why it should be a little different, but for now, let's just assume and entertain me on this idea that we are able to develop multiple decision trees on same training data. Now each tree a little different from others. Now how can we achieve difference in these trees? There are multiple ways to do this. The simplest way is to take only some selected part of the data, build a tree, take another part of data and build another tree, and that's how we can create multiple trees from same data, each a little different. We can also use different hyperparameters for each of the tree on same data for the tree to be little different, but the central idea is to create n number of models and to train these n number of models. So we fit n number of models to get n number of predictions, and if it's a classification problem we are attempting, then we take simply a vote among these n predictions and see which is the most popular prediction, and we call it our combined prediction. If we are attempting a regression problem, each of the prediction would be a number. Now these, because the models are different, the predictions might vary a little bit, and these would be series of numbers which would be slightly different from each other. The way to combine it would be we can average all these predictions out and get a combined prediction for regression type of problem. Now we get that we can create n number of models. Might be we are able to do that in such a fashion that each model is a little different from each other. We can also then train these models on that same data and get predictions and then combine predictions. But the central question you might have is, why would this work, or why should this work? Maybe of all the models that we would have developed, we have sight to all the predictions. You might ask, why can't we choose the model with best accuracy score amongst all these models? Might be there is that one model which outperforms all the other models. Why can't we select one best model and simply use that rather than using n number of models? Now it's a fairly valid question. Let's see. uh, I can give primary two reasons why a group of algorithms working together would almost every time outperform a single model, regardless how best it is. The first example is easier to understand. This would be by averaging. The first reason would be a little easier to understand. So by averaging multiple models, we would decrease the variance of the output. So it just takes out the randomness from the equation. So there might be a chance where the when you do test train split, just by chance, 1 in a million chance, that your test data ends up in such a way, or your training data ends up in such a way that model performs very very good. But often these models will not hold good when they are given unseen data. That means they don't generalize well. So to take off this randomness or just chance of model performing better out of our equation, and to be more certain that we can do this by stacking or layering together multiple models. Now the second reason why we should use an ensemble of models instead of one single model is it gives better prediction almost all the time. Now this is a little counterintuitive and a little hard to understand without taking an example. So let's see, by taking an example. So imagine, if you will, we're solving a classification problem where, given a features, our target is either a yes or no, 0 1, whatever it might be. It might be diabetic, non-diabetic, a malignant tumor, non-malignant tumor, or a species of flower. Target can be anything as long as it's a classification problem. Now imagine we have 10 different models, each with an accuracy of 70%. So each model has a 70% accuracy, would mean each model predicts the target 70 number of times correct out of every 100 times it is tested. So let's see how each of these model performs and what happens when we put them together in an ensemble and we average out the output. Let's see how we can benefit from it. So each model, let's say M1, is trained on this target and asked to predict. Now it might predict the first one correctly, second one wrong, third one right, fourth one right, fifth one wrong, and so on. But because the model accuracy is 70%, the model M1 would predict 70 out of 100 always correct. So you would always have, on average, you would have 70 of these correctly predicted. It would go wrong only 30% of the time on average. And same way with each of these models. Now remember when I said each of the model has to be a little different from each other, and this is why it has to be a little different, because if each model was the same, we would get the same, or every model would predict the same rows correctly and same rows incorrectly. But because these are different models, Each model, though predicting 70% of these correctly, the exact matches would be different. So while the first row is predicted correctly by model 1, model 2 might predict that incorrectly and might predict other rows correctly. But on average, given all the data, each model predicts the targets 70% of the times correct. Now, what we do in a typical ensemble learning is stack together all of these, pass the training data, get outputs from each of these, and then we take a vote. So something interesting happens here now. So given a model M1 is 70% accurate, model M2 70% accurate, we have each of these columns approximately 70% being correct. But for each row, this would have a chance of 70% being correct. This would have a chance of 70% being correct. That means at any given point of time, if we take an observation and if we take a vote, or if we count what are the maximum number of models saying, this would always be correct. And it goes on for the same by the same logic for every row. Even though individual models are only 70% accurate, if we average out all the models and see, and if we take a popularity vote or see, uh, if more than 50% of the models predict this to be a y, we count this as y. That ways we are always right. So somehow taking multiple models which are 70% accurate and combining them, we walk off with 100% accurate model. This is the central idea and intuition behind how ensemble method works. So as long as models are independent of each other, it does not matter even if models are weak, they are not highly accurate. A committee of these, or a group, a combination of all of these models taken together would act as much better predictor, and our ensemble of these models would have much higher accuracy than any single model together. Now, if you're not able to understand how I arrived at, so we understand that if a model is 70%, each of the columns should be about 70% right. If you want to convert this, if this is 70, this has the probability of 70% being right, and this has the 70% of probability being right, and this has a probability of 70% being right, how do you get a probability of the entire row being right? Now this is a very simple probability problem called a binomial distribution. If you want to read more about it, I have written a very nice article. It has been published at multiple places. I've provided a link on the slide. If you are interested, you can check that out. Okay, so now we have an understanding of why this works. It's okay to have multiple bad models, but combined together we get a strong model. As long as models are independent, weak learners will combine to get a good result. So the only constraint we are imposing is models have to be independent of each other, and there have to be multiple models working together. Now you see, as we stack up multiple models, our computation time goes up. So earlier when we were training one model, we used to take X amount of time. Now if we train 100 models, we would take 100 times that time. So usually the what people do is, when they are building these models, they don't allow these to be very complicated models. They take, it's okay, we don't care about the complexity of these algorithms, so we are okay with however they are. We don't spend much time tuning them, or changing the hyperparameters to see how well these perform. We just let these be, and then the computational gain we achieve by not tuning them by hyperparameters or not tweaking these models can be saved and used to combine these models together to achieve a far higher accuracy than what any individual model can. And this way, once we have individual predictions, we combine this, and that way we can use it for both classification and regression problems. Now, the way these models can be put together is sequentially or parallelly. The sequential connection of these models is often called bagging, and the parallel connections, I'll repeat it again. The sequential connection of these models, where these models act one after other. So imagine input being fed to a model 1, the output of model 1 fed to model 2, the output of model 2 fed to model 3. When they are connected in series, these are, or sequentially, these are known as boosting techniques. And if these are connected in parallel, that means simultaneously all of these models read the same data and produce outputs, and then we combine them. That means we are connecting them parallelly, and this is called a boosting technique. So next week we are going to cover random forests, and a week after that we develop a better intuition on both boosting and bagging techniques. Thank you for watching this video. If you like these videos, please don't forget to like and subscribe. Thank you.